Assalamu alaikum, dear students. So we meet again for today's lecture, and we will talk about where we left in the last lecture. In the last lecture, we mostly talked about the carrier concentration in semiconductors, which were pure, and we termed them as intrinsic semiconductors, as well as we talked about the carrier concentration in doped, that is extrinsic semiconductors, but keeping in mind that both in pure as well as extrinsic semiconductors, the law of mass action, that is the condition of thermodynamic equilibrium, was valid. Well, today we will enter into a new arena, namely where this equilibrium condition is disturbed in semiconductors, and thus leading to the non-equilibrium state or steady state, in which the carrier concentration is now not equal to the intrinsic carrier concentration. However, the state or the system tries to return to its equilibrium by another two dynamic processes, which we'll discuss in this lecture, and therefore this is the title of my today's lecture: the generation of charge carriers, free charge carriers, namely electrons and holes. And we discussed it many times before, that this generation of electron and holes takes place in pairs. So normally it is referred to electron hole pair generation. Similarly, the other opposite process which tries to bring back the carrier concentration towards its equilibrium value again is the recombination process. Thus the generation and the recombination processes are opposite to each other in semiconductor materials, and both electrons are produced in pairs. Similarly, in the recombination process, electrons recombine in pairs. However, I would like to stress that in both these processes, the rates of generation and the rates of recombination depend upon different parameters, which we will talk about in a minute. तो इस स्लाइड में आप देखेंगे कि मैंने तीन इम्पॉर्टेंट पॉइंट्स हाईलाइट किए हैं, जिनसे कि हम सेमीकंडक्टर्स में कैरियर्स को जनरेट कर सकते हैं. उसमें पहला और मोस्ट इम्पॉर्टेंट, जो हमने पिछले दो लेक्चर्स में भी जिनका जिक्र किया, वो है थर्मल जनरेशन, और दूसरा है ऑप्टिकल जनरेशन, और तीसरा है अगर आप सेमीकंडक्टर को नॉन इक्विलिब्रियम स्टेट में लेके जाएं बाय यूजिंग हाई एनर्जी पार्टिकल, दैट इज पार्टिकल बम्बार्डमेंट. अब सबसे पहले वाले प्रोसेस को लेते हैं, थर्मल इक्विलिब्रियम जनरेशन या थर्मल एक्साइटेशन ऑफ इलेक्ट्रॉन्स को. तो जैसे मैंने पिछली बार वजाहत करने की कोशिश की थी कि दिस थर्मल जनरेशन प्रोसेस इज टेकिंग प्लेस in semiconductor materials or in semiconductor devices all the time, because the crystal is maintained at a certain temperature. That is, the crystal is in thermodynamic equilibrium at the temperature which we had taken as a reference temperature. And to remind once again that the reference temperature that I had taken in my lecture is the room temperature, 300 Kelvin. Sometime photo excitation or non-equilibrium state is created in devices by shining light or bombarding photons on a given material or a given device. That is termed as excitation of electron hole pairs, that is excitation of electrons from valence band to the conduction band, that is the electron hole pair generation optically. And third, we can do the same process. We can achieve electron hole pair generation by providing energy to the bonded electrons by bombarding high energy particles onto a semiconductor material. So these are the three processes that we will be discussing in the following lecture. Well, to quickly revise what we had learned so far, that the carrier concentration, the electron concentration N, and the hole concentration P in a given material, whether it is intrinsic or doped, is subject to a condition known as condition of thermodynamic equilibrium. And mathematically it is stated as NP, the product of electrons, free electrons, and the product of free holes is equal to Ni square, where Ni square is the intrinsic carrier concentration, and mind you, this intrinsic carrier concentration depends upon the temperature and depends upon the band gap of the material. Again, as I said so many times before, in our lecture, in our following lectures as well, I had taken the room temperature as a reference point, which is 300 Kelvin, and the material being material under discussion is silicon, whose band gap is approximately 1.12 electron volt. When the system is perturbed, the system tries to restore itself towards equilibrium through recombination generation mechanism. Let me illustrate this term, perturbed. It's the same word which I mentioned before, that if we shine light on a semiconductor device which was previously under thermodynamic equilibrium, or if we bombard energetic particles on this material, then the generation rate of electron hole pairs will exceed than that of the rate of thermally generated electron hole pairs. In other words, in simple language, कि अब आपके पास एक्स्ट्रा इलेक्ट्रॉन होल पेयर जनरेट हो रहे हैं लाइट शाइन करने की वजह से या एनर्जेटिक पार्टिकल बम्बार्डमेंट की वजह से, बनिस्बत उसके जो कि थर्मली आपके इन एनी केस जनरेट हो रहे थे पहले से सेमीकंडक्टर मटेरियल में. सिलिकॉन में एट रूम टेम्परेचर हमने पहले भी बताया कि ये नंबर अप्रॉक्सीमेटली 10 to the power 10 पर क्यूबिक सेंटीमीटर है, लेकिन अब ये नंबर बढ़ जाएगा क्योंकि हम लाइट शाइन करके एक्स्ट्रा कैरियर्स इलेक्ट्रॉन होल पेयर जनरेट कर रहे हैं. इसी तरह हम पार्टिकल बम्बार्डमेंट से एक्स्ट्रा कैरियर्स इलेक्ट्रॉन होल पेयर्स जनरेट कर सकते हैं. ऑब्वियसली ये जनरेशन रेट डिपेंड करेगा फ्लक्स ऑफ द इंसिडेंट फोटॉन्स पे और एनर्जी ऑफ द पार्टिकल्स विच यू आर बम्बार्डिंग. तो फिर क्या होगा, जो डिवाइस आपकी या सेमीकंडक्टर मटेरियल जिस पर कि आपने अभी लाइट शाइन नहीं की थी या पार्टिकल बम्बार्डमेंट नहीं की थी, उस वक्त वो थर्मोडायनामिक इक्विलिब्रियम में था. लेकिन लाइट शाइन करने के बाद यानी फोटोन बम्बार्ड करने के बाद या पार्टिकल बम्बार्डमेंट के बाद it goes into a state which we term as a state of non-equilibrium. और फिर क्या होगा, नॉन इक्विलिब्रियम में जाने के बाद ये सिस्टम या इलेक्ट्रॉन होल पेयर की कंसंट्रेशन विल ट्राई टू रिटर्न टुवर्ड्स इक्विलिब्रियम स्टेट. और इक्विलिब्रियम में कैसे वापस आना चाहेगा, वो ऐसे कि जनरेशन की वजह से आपने कैरियर्स की कंसंट्रेशन बढ़ा दी. अब सिस्टम में, डिवाइस में, मटेरियल में इलेक्ट्रॉन होल पेयर की तादाद दोबारा अपनी इक्विलिब्रियम वैल्यू की तरफ आना चाहेगी. तो जाहिर है आप क्या करेंगे, किसी मैकेनिज्म से उन फालतू इलेक्ट्रॉन होल पेयर्स को जो लाइट ने या पार्टिकल्स ने क्रिएट किया, आप उनको एलिमिनेट या ख़त्म करना चाहेंगे. द प्रोसेस इन सेमीकंडक्टर्स विच रिड्यूसेस दीज एक्स्ट्रा इलेक्ट्रॉन होल पेयर नंबर इज termed as the recombination process. Thus, the generation process and recombination processes are opposite to each other. Generation creates extra electron hole pairs. Recombination eliminates those extra produced electron hole pairs, and thus in such a way the device tries to return to its equilibrium value. In a minute we will discuss that there are various parameters upon which this return of the device from non-equilibrium or steady state towards equilibrium state depends. So it depends, the return towards equilibrium state by the recombination process depends upon certain parameters or factors. One of the important factor is the carrier lifetime, which we will talk about in a minute. That is what I have stated. We will calculate the steady state rates by which the extra generated electron hole pairs are eliminated by the process of recombination. This rate will be proportional to the deviation from equilibrium. जैसा मैंने अभी बताया कि n dot p is equal to ni square. आपकी कंडीशन थी इक्विलिब्रियम में, जिसमें n फ्री इलेक्ट्रॉन कंसंट्रेशन है और p फ्री होल कंसंट्रेशन है। चाहे मटेरियल p टाइप हो तो जाहिर है उसमें p टाइप में होल्स मेजॉरिटी में होंगे और इलेक्ट्रॉन माइनॉरिटी में होंगे। अगर मटेरियल n टाइप है डोप करने के बाद तो इलेक्ट्रॉन्स मेजॉरिटी में होंगे, होल्स माइनॉरिटी में होंगे, मगर मेजॉरिटी और माइनॉरिटी दोनों का प्रोडक्ट फिर भी ni² रहेगा। अब अंडर नॉन इक्विलिब्रियम कंडीशन या स्टेडी स्टेट कंडीशन में हम क्या कहते हैं कि हमारे पास ये प्रोडक्ट थोड़ा सा फ़र्क हो जाएगा, यानी एक्सेस कैरियर्स आ गए। तो कितने एक्सेस कैरियर्स आ गए वो बॉटम इक्वेशन में आपको नज़र आ रहा है, Np माइनस ni²। तो जो एक्सेस आपके पास आ गई, अब लाइट शाइन करने के बाद मटेरियल में उसका रिकॉम्बिनेशन रेट जाहिर है किस पे प्रोपोर्शनल होगा कि जितने ज़्यादा कैरियर्स आपने डाले मटेरियल में, जितने ज़्यादा कैरियर यानी इलेक्ट्रॉन होल पेयर आपने क्रिएट किए बनिस्बत उसके जो आपके इक्विलिब्रियम स्टेट में मौजूद थे, तो रिकॉम्बिनेशन फास्टर होगा अगर ज़्यादा कैरियर जनरेट किए। और अगर आपका जनरेशन रेट इतना ज़्यादा नहीं था तो रिकॉम्बिनेशन भी उसी मुताबिक से एडजस्ट हो जाएगा। So we say mathematically that recombination is proportional to the excess electron hole pairs generated in a given semiconductor material at a given temperature T, and the proportionality constant is A. We will discuss in a minute about this proportionality constant. In generation of electron hole pairs in the semiconductor materials and the recombination process again in the semiconductor materials, I would like to make an important note here that in both the processes the electrons as well as holes are generated as well as eliminated in pairs, because this process of generation of electrons and holes thermally or optically or by particle bombardment is different from the charge carriers which you obtain by ionization of the dopant impurity. So we have to make a distinction between the charged particles or charge carriers obtained by adding the dopant impurity, because there you only get a single type of charge carriers. If you add donor impurity in a pure material, in the intrinsic material, you only get electrons. And if you add acceptor impurity, then you only get holes. While in a generation process, the generation process is termed as the mechanism in which bonds are broken, in which silicon bonds are broken, and thus electron gets free, and in terms of the band structure of the crystal, we say it is now found as a free electron in the conduction band, and thereby leaving a vacancy or unbonded or in incomplete bond, covalent bond in silicon crystal structure, and that vacancy is termed as hole. Thus, in generation process, both the carriers are generated in pairs, and this is a difference between charge carriers obtained from dopant impurity and generation process. Thus, in generation process, electrons and holes generate equally and recombine equally. This generation and recombination process is important in the study of operation of devices, because that is the basic and fundamental dynamic process which is taking place in devices which are operating under non-equilibrium conditions or steady state conditions. A famous device known as photodiodes, LEDs and laser, all these devices are based on the mechanism of generation as well as recombination of charge carriers. Similarly, we will see that in the basic device, which is the p-n junction or simple semiconductor diode, again this the current flow or conductivity in the junction is dependent on the generation and recombination rates in the device. Generation, again, to put it down in black and white, I had just explained, generation is the term or is the process in which covalent bonds of the silicon crystal are broken and hence electron hole pairs are obtained. Similarly, in the recombination process, a free electron from the conduction band moves down to the valence band and recombines or gets bonded again in its covalent bond. So generation and recombination processes are opposite to each other. In the middle of the transparency, you see, obviously, you will appreciate that for generation, you have to break a covalent bond. And in order to break the covalent bond, you require energy. This energy is of the order of only about 50 MeV or so for most of the semiconductor materials. Let's say in silicon, it's of the order of 50 millielectron volt. Now this energy is sufficient to generate thermally generated electron hole pairs using the effective mass approximation. That's the thermal generation process. But from band to band generation process, we require, for the ionization energies in the dopant impurities is very small, of the order of 50 millielectron volt. Thereby, as we stated earlier, the added donor impurities and added acceptor impurities are mostly ionized. To a first approximation, we can say that the electron concentration from the dopant impurity is almost equal to the concentration of the donors. The whole concentration in p-type material is almost equal to the acceptor impurity at room temperature, because room temperature thermal energy, as we calculated already, is 0.025 electron volt, which comes out to be only 25 millielectron volt. While using the hydrogenic model and incorporating the effective mass approximation, we calculated that the energy required to free the extra electron from the fifth impurity, the covalent fifth electron from phosphorus, requires only 50 MeV, 50 millielectron volt. So this energy can be obtained at room temperature. The thermal energy can ionize these impurity atoms. But on the other hand, if we now compare the generation, band-to-band generation, that is the electron hole pair generation process, then the energy required obviously is equal to the band gap, because the electron is now jumping from valence band to the conduction band. And in order to raise the electron from valence band to the conduction band, we require energy equal to the band gap. This energy can be supplied, I've listed 3 processes in terms of thermal energy, or in terms of optical energy, or in terms of particle bombardment. Now this thermal energy has to be equal to the band gap. Now the temperature has to be high enough so that it can give enough energy to the electrons. Optical generation for photons, the photon energy has to match exactly equal to the band gap, because it is a quantum mechanical process. Similarly for particle bombardment. For thermal energy, it's a different story, because there the thermal generation rate depends upon the thermal energy kT as well as the band gap. So there is a finite probability for that. Next, we move on to discuss what I just mentioned, that the band gap is an important parameter which we have to take into account while dealing with optical generation of electron hole pairs in semiconductors, because the photon energy has to match the band gap. How do we express this in terms of the covalent bond picture, in terms of the crystalline structure of silicon? The covalent bonds are broken, and an electron moves by hopping to a neighboring bond. Because of the Pauli's exclusion principle, it has to be lifted into the higher anti-bonding state of that bond. In the picture of delocalized states, for example, in one dimension, that is a nanowire, for every energy there is a state with electrons flowing in one direction and one state for the electrons flowing in the other direction. In terms of the band gap, again we make a distinction that for most of the materials which we classify as semiconductors, the band gaps are narrow, ranging from about half an electron volt to about 2 or 3 electron volt. Gallium phosphide having a band gap of about 2.25 electron volt, while insulators are classified as those materials in which the energy band gap is of the order of 6 to 7 electron volt. Here is a schematic representation of the process of generation as well as recombination. Earlier we made a distinction that for generation you give energy to the electron which are bonded in the covalent bonds, or in terms of energy band diagram shown here, which are now bound in the covalent band, in the valence band. You give the energy to the bound electron in the valence band either optically or by raising temperature or by particle bombardment, and thus the upward arrow indicates that the particles, bound electrons, are lifted to the conduction band where their state is now termed as free electrons, and leaving behind a vacancy which is termed as a free hole. And this process, the yellow arrow indicates, this process requires energy. That is, band-to-band transition in the generation process must be subject to some conditions and laws. Similarly, in the recombination process, you see the downward arrow in which the electron, free electron from the conduction band, now moves to the valence band where it becomes, where it recombines with the hole, and thus the electron gets bound. Just as we appreciated that in thermal generation process you require energy, in the same way when recombination takes place you have to conserve this amount of energy, and this energy therefore some amount of energy is released, which we will talk about whether in a minute, whether this energy is released in the form of photons or some particles or dissipated in some other mechanism. So thermal generation and thermal recombination processes obey certain distinct rates depending upon. Recombination rate depends upon the availability of the free electrons in the conduction band to recombine with the available free holes in the valence band. If there are very few electrons and very few free holes, obviously the recombination rate would be slow. Similarly, for generation process, if the band gap is too high, recombination rate will be slow, because obviously you require a large amount of energy, optical energy, let's say, to match the band gap. In this transparency, in this slide, I have tried to give you some quantitative idea how much energy is needed by the photon, let's say in optical generation, by the photon enabled to create an electron hole pair. Let's say the photon energy is of the order of 2.06 electron volt and the band gap is approximately 2.5 electron volt. What do you think will happen? The photon will not be able, because the photon energy is less, it will not be able to lift the bound electron to the conduction band from the valence band. Hence the photon will not be absorbed by the semiconductor material whose band gap is 2.5 electron volt, or there will be no electron hole pair generation. In the middle of the diagram, the photon energy is the same. Same photon energy is now bombarded, let's say on a crystal whose band gap is 1.5 electron volt, you can see that the photon energy is greater than the band gap. What will happen? As you see in this diagram, now the photon energy is greater, so it can break the covalent bond, thereby lifting the bound electron to the conduction band. So what do you get? A free electron in the conduction band or a free hole in the valence band. Hence the process of electron hole pair generation has taken place. Similarly, in the bottom diagram, you see again the phenomenon is that you have extra energy supplied by the photon and the band gap is smaller. So the extra energy which is now left after freeing the electron from the covalent bond now becomes the kinetic energy of the electron in the conduction band. So electron in the conduction band not only has been freed, not only the electron has been generated, it also acquires enough kinetic energy to be placed in higher states in the conduction band, within the conduction band. In the bottom of the slide, I have tried to explain how the photon energy is related to its wavelength lambda, so that you can calculate in terms of the band gap energy how much energy of the photon, that is what should be the wavelength of the photon in order to generate photo-generated electron hole pairs compared to a given band gap of a semiconductor material. Let me explain in detail the recombination process again. Recombination is the opposite of generation, as we described many times just now, which means this isn't a good thing for photovoltaic cells, but because it leads to loss of current. So we want to avoid processes, recombination processes in device operation where we do require large number of electron hole concentration. So you should try to avoid the recombination processes in devices, particularly in photovoltaic devices. Recombination is most common when impurities or defects are present in the crystal structure and also at the surface of the semiconductors. Let me explain this a little in a little simpler way. In the top, I said that recombination processes are not desirable all the time in some of the semiconductor devices. How do we understand recombination? In the previous two slides, I had shown only band-to-band recombination. That is, the electron, free electron from the conduction band jumps down to the valence band and recombines with a free hole present. In most of the semiconductors, whether they are intrinsic or extrinsic, that is not always the case, because semiconductor materials or semiconductor devices also have all sorts of impurities. The most common impurity is the dopant impurity, which we added deliberately in a material to make it either N-type, which is the dopant impurity, or P-type, which is the acceptor impurity. And by now you understand that the donor impurity is ionized, and similarly acceptor impurity is ionized because they have already donated their extra electron. The donor impurity has already donated its extra electron. Similarly, acceptor impurity is also ionized. So you have ionized donors and you have ionized acceptors, which act as sources with which electrons and holes, through which electrons and holes can recombine. But the donor and acceptor impurity levels are in fact too close to the conduction band and too close to the valence band respectively. So these the so-called shallow level impurity levels, shallow level dopant impurity levels, actually are not so significant for the recombination process. I just mentioned them so that you understand that the donor and acceptor impurities are present in the semiconductor material, and their presence will be more significant, will be more effective when we discuss the process of drift and conductivity and mobility in the next lecture or so. But I just mention it at this point because in a minute I will talk about other impurity atoms present in the semiconductor crystal or semiconductor device. These are impurities other than the dopant impurities in the material. And the most effective way for recombination is for the impurity to be somewhere in the middle of the band gap. So what happens that electrons makes a transition from conduction band to this deep level impurity center, and then from there it goes to the valence band. Thus the recombination process takes place in 2 steps, and thereby making recombination easier in some of the devices. And thereby the band gap is seen to be broken as if it is broken in 2 parts. First part being the transition from conduction band to the impurity or defect center, and from defect center to the valence band. Just as we explained before, in thermal generation or optical generation or particle bombardment generation, that is in any kind of generation in which electrons are raised from valence band to the conduction band, in the process in which bonds are broken, you require energy. And that energy, we had already mentioned, should meet certain requirement. Similarly, for the recombination process, you have to conserve this energy when electron returns from conduction band to the valence band. There are 3 important mechanisms which we will discuss at this point. Number 1 is that energy is dissipated, is emitted not in the form of photons but in the form of phonons, which are lattice vibrations. So the electron does recombine, the energy is emitted, but a photon is not emitted. Let me explain it once again. In photogeneration, you bombard a photon onto a given semiconductor material or device. So it's a photogeneration, but it is not necessary that the same photon should be emitted or photons should be emitted when the photogenerated electron and holes recombine, because of course conservation will take place, but not through radiative emission. Radiative emission in simple terms is a process in which photons are emitted or electromagnetic radiations are emitted. So if there is no photon emission, there is no electromagnetic emission, where does this energy go? This energy goes or is emitted in the form of lattice vibrations, which we term as a phonon emission in quantum mechanical terms. The middle process of energy emission is common, which is the emission of photons, and this process is termed as radiative recombination. Auger recombination is another interesting process, which is that instead of phonon emission or instead of photon emission, the energy is directly transferred to the nearby electrons which were bonded or bound before, and therefore an electron is emitted due to this energy release in the recombination process, and this is the Auger emission, that is the emission of electrons. So to summarize again, we have photon emission. Following a recombination process, we may have phonon emission and we may have the Auger emission. The probability in most common semiconductors is the phonon emission, and that leads us to another process, which is the direct bandgap materials and indirect bandgap materials. I have tried to explain these processes in the following 3 slides in slightly larger detail. Here is another illustration and a colorful illustration of what happens in a recombination process, that if an electron from the conduction band recombines with a hole in the valence band, you get photon. This transparency shows the emission of radiative recombination, and this photon emission can be utilized, can be incorporated in devices which are termed as light emission devices, light LEDs or lasers. In the previous 2 or 3 slides, we talked about the emission of energy or release of energy in a recombination process, and we tried to explain 3 mechanisms, 3 important mechanisms by which this energy can be accounted for. The most common, as I said before, being the phonon emission, which is termed as a non-radiative process. The second, what you understand very easily, which is the radiative or photon emission in a recombination process. And third, the Auger emission, that is the electron emission in a recombination process. Now, which of the 3 processes will have a higher probability, or which 3 of the processes will be most likely to happen, will depend upon not only the band gap energy, but also on another parameter of the band gap, which is termed as the EK space. Now, in the EK space simply means the energy versus momentum vector of the crystal lattice. Here on the left side of the picture, you see again the same energy band diagram, but now instead of the flat energy band diagrams with which we have been used to so far, we have a schematic illustration in which there is a curvature. The direct band gap materials are classified as those materials in which the conduction band minima lies exactly on top of the valence band maxima. Therefore, the electron makes a transition. It's easier for the electron to make a transition from the conduction band minima to the valence band maxima, and thereby creating or leading to a recombination process. In the band gap material, in the direct band gap materials, thus there is the momentum conservation as well as the energy conservation, as you can appreciate in this transparency on the left hand side. And this type of photon emission, as we already said before, this type of photon emission can be used in fabricating LEDs and lasers. So the most important point here, which we are making for the first time, is not only we are trying to understand whether this energy in recombination process is emitted in the form of phonons or in the form of photons. This is directly related to the energy band diagram or EK diagram of the semiconductor material as well. It's not just the band gap, it is the position of the conduction band and the position of the valence band also are significant now in terms of the EK diagram. Here is the same phenomenon now shown for the materials which are termed as indirect band gap materials. In the indirect band gap material, as you can see in this schematic illustration, the conduction band is displaced from the valence band. What is going to happen? Even though there might be conservation of energy, but the momentum conservation is violated, and hence for such materials the probability of the photon emission is negligible, and what do you get? The probability of phonon emission will be larger as compared to probability of the photon emission. So we say that for an indirect band gap material, the minimum of the conduction band and the maximum of the valence band lie at different values of K. When an electron and hole recombine in an indirect band gap semiconductor materials, the probability of phonons is higher, because phonons must be involved to conserve the momentum. What are phonons? Phonons can be visualized as atoms vibrating about their mean position at a finite temperature. These vibrations produce vibrational waves inside the crystal. Phonons are the quanta of these vibrational waves. Phonons travel with a velocity of sound, and their wavelength is determined by the crystal lattice. Phonons can only exist inside the crystal. Now let's sum up what is written on the right side of this transparency. As you see on the left side of this slide, that the momentum will not be conserved in a transition known as recombination. So we introduce another term, that phonons are emitted, that is, the lattice now vibrates, and the vibration rate or the vibration frequency now would be dependent upon the temperature of the crystal, because you are familiar from your fundamental knowledge of the vibrational modes that as the temperature increases, the vibrations of the lattice atoms is enhanced. So phonons emission would be dependent upon the temperature of the crystal as well. In the direct band gap material, the minimum of the conduction band and the maximum of the valence band lie on top of each other. Therefore, the momentum is conserved. When an electron in this, you can see in this slide, makes a transition from conduction band to the valence band, there is conservation of not only the momentum but also that of the energy. Here is another representation, another illustration of band-to-band transition, band-to-band generation, as we explained before in many transparencies, that you can raise electron, bound electron, from valence band to the conduction band by supplying thermal energy, or by supplying by bombarding photons or shining light onto a device. In the recombination process, you have electrons coming to valence band, and they are recombining with a hole in the valence band, and this transition may take place in the via the impurities or defects present, whose position within the band gap, as I explained or mentioned before, the probability will be higher if this trap or impurity center is somewhere in the middle of the band gap. Since I'm showing this slide only for the generation process and not the recombination, so the upward transition, that is the bound electron from the valence band, first goes to a state termed in this slide as ET, that is the energy of the trap center, and then from there it makes a transition to the upper conduction band. So the transition takes place in two steps, in contrast to the direct band gap, where a single jump, where the electron makes a single jump from valence to conduction band. Now it makes a two-step transition from valence to conduction band. Similarly, the impact ionization, which will be discussed in detail later on when we discuss the avalanche breakdown. The same reverse process now as we discussed for generation. Here in direct band gap material, the recombination is directly from the valence band to the conduction band. Energy is emitted in the form of photons or phonon. In this picture I have shown the emission of radiation in the form of photons, that is light emission, and therefore your LEDs and lasers are based upon the recombination mechanism in which the probability of photon emission is higher than the probability of phonon emission. The middle slide shows the recombination process via your ET, that is the trap centers. The most likely process by which energy is dissipated or conserved is the thermal energy. And similarly, in the Auger electron process, now instead of photons or phonons, a real particle, that is a bound electron, receives that energy which should be emitted from recombination process. Hence, an electron is emitted, a bound electron is emitted. The electrons in the outer shells of the silicon atoms are emitted, and they are covalent. They are Auger electrons. Let's now do some mathematical analysis. Let's try to understand in our mind some concepts of relating the energies of photons and phonons with the band gap of the material, because by now I'm quite sure that you understand how much energy is needed in order to generate electron hole pairs, either by using photons or by enhancing the crystal temperature or by bombarding, let's say, protons, energetic protons onto a device, and how much energy would be released if the recombination takes place via photon emission or via phonon emission. So let's take the example of gallium arsenide now. Why I have chosen gallium arsenide? Because its band gap is somewhere in the middle of the silicon, whose band gap is 1.1, and that of gallium phosphide, which is more than 2 electron volt. Okay, the band gap of gallium arsenide is 1.43. Gallium arsenide is a 3,5 compound. That is, gallium belongs to the third group of the periodic table, and arsenide belongs to the fifth group of the periodic table. So gallium arsenide is an important semiconductor material because it has in between band gap energy of the order of 1.43 electron volt. By using the simple law E is equal to h nu, we can calculate the wavelength of the photons which will be emitted, and we notice that it will be about 0.88 micron meter. Photon corresponds to the band gap energy of the semiconductor material. So if we shine light on gallium arsenide, whose photon energy is equal to 1.43, it will have a wavelength, the photon will have a wavelength of about 0.9 or 0.88 to be exact micron meter. Thus the photon would have a momentum of the order of this value, which is shown in the slide. So in a direct band gap material, in a direct recombination process, a photon, which if you shine a photon, it can have energy, it must have a threshold energy greater than band gap. And in the recombination process, if the recombination energy is exactly equal to the band gap energy, then the photon momentum and the photon wavelength are given on the left side of the slide. If, however, photon is not emitted, that is, the recombination transition does not take place via radiation emission, but the recombination is what we called before as a non-radiative recombination, that is, phonons are now emitted, then let's look at the phonon energy. The phonon energy, because is now seen as a phenomenon in which the lattice atoms are now vibrating. So vibrational modes are now termed as phonons. So it is subject to the phonon parameter of phonon energy or wavelengths are now matched with the lattice constant of a crystal. And hence we calculate by using these two simple parameters that the photon energies are of the order of 37 milli-electron volt, and phonon momenta are again shown at the bottom of the slide. So we notice the difference, we can appreciate the difference, that large amount of energies are associated, or photons carry almost energies almost equal to the band gap, while phonon energies are very, very small, of the order of milli-electron volt. Hence a large number of phonon emission takes place in order to conserve or dissipate the recombination energy in a recombination process. I have summarized the same two quantities again now for photon as well as phonon. So photons carry large energies but very small amount of momentum. On the other hand, phonons carry a very small amount of energy but significant amount of momentum. So these are two important distinctions between photon emission and phonon emission, that is radiative emission and non-radiative emission in a recombination process. What is photo recombination? Now I try to explain in terms of the schematic illustration. As we mentioned before, the threshold energy, that is the minimum energy that the photon must have or is required, should be equal to the band gap. As we saw in an earlier slide, that if the photon energy h nu or E photon is less than the band gap, then it will not be able to generate electron hole pairs. But if it matches exactly, fine. And if it is greater, then again there is no harm. The extra energy greater than the band gap goes to the kinetic energy in the form of kinetic energy of the electron. So we have two-step process or two-step generation, and similarly two-step recombination in a photo generation or photo recombination. That if the photon energy is higher than the band gap, then the photon can be elevated or raised to a higher state within the conduction band, or it can be raised to at the edge of the conduction band or minimum level of the conduction band, and the extra energy can be dissipated in the form of phonons. Another different transparency which is used for calculating that if you shine a light having intensity I naught, that how many photons will actually generate electron hole pairs, or how many photons will actually create electron hole pairs, because it is not necessary, it's obvious that not all the photons will be able to generate electron hole pairs. Some of them will be transmitted without generating any electron hole pairs. So this transparency explains that if you shine a photon having energy equal or greater than the band gap of the material, some will be absorbed, within quote, absorbed by the material. When we say absorb, we mean they will generate electron hole pairs. The photons which do not generate electron hole pairs, they will be transmitted by the device, and hence the transmitted photons, that is those photons which are not able to generate electron hole pairs, will be expressed in terms of an exponential factor. And you see that this decrease is proportional. The numbers of photons which will cause electron hole pair generation will depend upon the thickness. The greater the thickness of the material, obviously more and more photons will be absorbed, Hence, the relationship at the end of the slide shows that the decrease, that is the absorption, is exponential, and it is proportional to the thickness I, to the thickness L of the semiconductor material. Now we can write down a mathematical relationship in steady state, that what is the photo generation rate. Photo generation rate, that is the rate of electron hole pair, rate of excess electron hole pair in a semiconductor material, is proportional to the thickness as well as on some other parameter, where GLO is the photo generation rate. Now I have posed a question: what happens if the energy of the photon is less than the band gap energy? You should be able to answer this question at this stage, because photo generation is the process in which light is shown, or a photon is bombarded on a semiconductor material in order to raise the electron from valence band to the conduction band. So what will happen? What do you think, what do you expect if the photon energy is less than the band gap? So your answer should be that it is not able to, this photon whose energy is less than the band gap of the material will not be able to generate an electron hole pair, namely the photo generated electron hole pair. Here is a calculation which should be interesting for you to correlate with the photo generation and the ionization of the dopant impurities. At room temperature, you only have about 25 milli-electron volt. For room temperatures, the energy, thermal energy at room temperature is about 25 milli-electron volt, because the calculation is on the top line of this slide. This thermal energy, room temperature thermal energy, is comparable to the ionization energies of the dopant impurities chosen from third group of the periodic table or from the fifth group of the periodic table. So you see that 25 milli-electron volt is a small amount of energy which is available to the crystal anyway at room temperature. In contrast, if we want to generate a photo generated electron hole pair, then the energies must be of the order of the band gap material, as you see in this transparency, that the photon wavelength corresponding to silicon, whose band gap is 1.1 electron volt, then the wavelength is 1.1 micron meter, and therefore this band gap 1.1 electron volt lies in the infrared region. That is, if we shine light, we require energy, photon energy must be equal to 1.1, and upon recombination, if supposing there was a direct band gap recombination, the photons, if there is a photon emission in silicon, if the free electron makes a direct transition to the valence band, then the photon that would be emitted, let's suppose, will also have 1.1 electron volt energy. If we convert this photon energy into wavelength, then the wavelength will correspond to 1.1 micron, which is in the infrared region. What I'm trying to explain in this slide is that silicon, obviously, even though our most favorite semiconductor material, even though available abundantly, is no good as a device material where you want light, the light, that is the photon in the visible spectrum of electromagnetic radiation. Hence, LEDs cannot be fabricated, cannot be made by using silicon material, because the energy which is going to be emitted is in the infrared region. So when we come to discuss LEDs, we have to make appropriate choice where the energy released in recombination process must lie in the visible part of the electromagnetic spectrum. I would like to end at this point and elaborate these recombination and generation processes further when we discuss the operation, when we move on to the second part of our lecture, which is the device operation. And the devices which we will be talking about in future would be the PN junction or the simple diode, bipolar junction transistor, so on and so forth, field effect transistors, etc., etc. So now that we understand the recombination and generation processes taking place in semiconductors, which are now termed as in steady state or non-equilibrium conditions. So we summarize that generation and recombination processes affect carrier concentrations as a function of time and thereby current flow. The recombination, that is the elimination of excess carriers introduced by generation, will be a function of time, and recombination will also be a function of, is strongly dependent upon the carrier concentration. Generation rate is enhanced by deep near mid-gap states. What does this point illustrate? As I mentioned before, to raise an electron, bound electron, from conduction band to from valence band to conduction band, if there are no middle states within the band gap, will require a large amount of energy. But if there are intermediate states, then the generation process can be made easy and the generation rate will enhance if the electron can make transition in 2 steps rather than in 1 step, as in the case of band-to-band transition, which we showed in different slides earlier. Recombination in silicon is primarily via recombination generation centers. Why is that? Why have I summarized it in the following manner? Because silicon is not a direct band gap material. Therefore, in order to conserve the momentum in the energy band diagram, we introduce, or sometimes there are imperfections, the lattice imperfections, there are impurities already present in the silicon without our intentionally adding them there. So this recombination process takes place through recombination generation centers, and in silicons that's the most common mechanism because it is an indirect band gap material. For the recombination processes in which the recombination takes place through the recombination, the middle states known as the impurity centers or recombination generation centers, the decrease of excess carriers through recombination process is proportional to the lifetime of the minority carriers, and this we will see later on in other lectures as well. Obviously, lifetime is a characteristic or is a parameter of the material as well as how many extra carriers you have introduced. In simple terms, it simply states that for how long these additional carriers which you have generated, which you have put in through photo generation or thermal generation, will last, will stay in the material, will live in the material before they recombine again. And this time for which extra electron hole pairs are present in the material is termed as the carrier lifetime, the minority carrier lifetime. And generally the net recombination rate is proportional to the density of the traps, that is how many steps there are in between the band gap, and it is also proportional to the probability whether a step will be willing to accept the free electrons from the conduction band and then release them to the valence band in order to accomplish our recombination generation, recombination as well as generation process. So thank you very much for being with us for this lecture, and I shall inshallah see you again for the next lecture. Thank you so much.